It's my pleasure to introduce Aditya Mehra, who will be discussing Immortal Objects.
Hi. Thanks a lot. Good afternoon, guys. So today we are discussing about introduction of Immortal Objects in Python language and how it is going to be a building block towards a multi-core Python runtime. Hi, I am Aditya Mehra. I am a software architect as a profession. I have a keen interest in yoga and meditation. And along with work, I am supporting community with teaching impoverished kids in technology and soft skills. I am an active member of Python Software Foundation and actively involved in volunteering and other activities for PyCon and other Python-related activities. And a father of two lovely kids, which are there. Yeah. So refresher, so summary is, we would like to be discussing on refresher on Python objects, some refresher on Python memory management, what is the motivation and use case for PAP 683, that is the base of changing the basic data structure of an object in Python. What is the impact and what is the future plan? Okay, so refresher on Python objects. As we know, everything in Python is an object. What does that mean? I will explain you what does that mean. But the thing is that for now, you can see that in my screen, I put from my dev machine, which is having 3.12 version of Python. As you can see, I tried to compare every class, a normal class, integer, float, dictionary, lambda, or even a type, and compare, like, check that is it an instance of object or not, or it is an object or not. Yeah, everything is object. In Python, everything is treated as an object, including lists, sets, all these. So yeah. So what does that mean? An object means in a higher level view, it should be having a place in a memory. Okay? Also, it should be having a state or data. Also, it should be having a data type. For instance, here what I am doing in the screen is, it depicts that I've created a variable, var1, and assigned a value, hello Python. Internally, what it does is, interpreter or runtime, what it does is, it assigns a memory address. It allocates a memory address actually, and assign that value, put that value over there in that box. That is called state and data. And it dynamically checks that what is the type of this data. It identifies that string and put it over there. And most important, it created a reference. As you can see, var1 is referencing to that particular memory location. Why I am refreshing all you guys about this basic operating system and memory management, because it will be based to understand what are the changes which we have done, Python developers have done internally, to the basic data structure of that object, and why was it needed. Also, I would like to throw some light on the type of the references. So I already mentioned references. However, what we are doing here is that increasing the reference count. So when, for specifically here, for a string, when I created a var1, it allocates some memory location, it puts the value over there, and it tells that var1 is referencing to that particular memory location. But what I'm doing here, I went further. I'd assigned that variable var1 to var2 and var2 to var3, as you can see on the right-hand side in the picture. And same thing I did in the code in the left-hand side. So I will go from the top to down, the code, to explain more here. To check the reference count. Reference count means for that particular memory location, how many objects or how many variables are looking for that or having reference to that particular memory location. So I imported C types, a module, inbuilt module in Python. Before that, after I assigned a variable var1 equal to hello Python, and curiously I checked that what is the memory location which is being assigned, which is var1 is referencing to. So I found that number ending with 327624. After that, I use C types dot C long from address, and I provided that address and tried to get the value. It's provided me 1. What does that mean? It means that right now, in my environment, in my dev environment, with that, for that particular memory location, there is only one reference, var1. After that, what I did, as I mentioned, depicted in the screen on the right-hand side, var2 is being assigned the var1. So internally, it takes that it does not create another memory location. It's just a assignment. So what it did, it created one more reference. Now I try to get the reference value. So it is now 2 now here. After that, I did var3 equal to 2. And var3 is also pointing to same memory location. And when I try to get the now reference to that particular memory location, it is 3 now. OK. So we are clear with this. Though in the previous slide, we tried to increase the count. Now what will happen when we decrease the count, reference count? And the reference count can be 0 or can be decreased based on if the variable is de-scoped, out of scope. For example, when you create a function, inside that function, you create a local variable. When you come out of it, there should be dereference, the reference should be 0, and there should be GC, garbage collected. I will explain much more about it. Okay, so here what I am doing, I explicitly deleting the variables one by one. In short, I deleted var3. I checked that what is the reference count, 2. Deleted var2, 1. Deleted var1, reference count 0. Now it is a suitable candidate for garbage collection. That is a mechanism which is based on the reference count. And we do not need to worry about the memory management. It is done by most of the programming languages in Python. It is being done by the reference count. And when the reference count becomes 0, it becomes a candidate for garbage collection. Also, what I found interesting, like my version is 3.12. What I did, I created, I assigned some singleton data types like false, none, booleans. So interestingly, the reference count was -1. I will explain like why it happened. So the object lifecycle looks like this. So object lifecycle is like a creation. So objects are created dynamically in Python using constructor or literals. When an object is created, memory is allocated for its data and any necessary internal structures. A reference is being created. Second point is reference. Objects are being referenced by variables, data structure, or other objects. Dereference, object out of scope, or we delete explicitly. Garbage collection, if refresh count becomes 0. Destruction, we can add dunder, del, and dunder, but it has an unpredictable behavior, so we should not do this. And after that, there is one more cycle comes, finalization, where real memory flushing out happens and memory reclamation happens. So garbage collection is the language runtime tracks how many references are there. And I will show you the code also. You will get an idea what I'm talking about. And just keep in mind that this thing happens. Yeah. And when code takes ownership of a reference to an object or releases, the runtime is notified and it increments or decrements the reference count. As I mentioned, the reference count becomes 0. It becomes candidate for the GC, garbage collection. Yeah. And now, mutable. So one more thing I would like to throw some light is mutable and immutable objects in Python. This is the, I created a list where integer are immutables, list and sets are mutable, dictionaries are mutable. What is immutable? An object is considered mutable if its state or value can be modified after it is created. Okay? And I'll quickly go through. Immutability is the when no change is possible over time. In Python, if the value of an object cannot be changed over time, then it is known as immutable. So when we create a string, for example, and when we append or create, when we try to, we cannot, first of all, we cannot change that string like an array. If we want to append like hello and append a world on it, a new string, the new memory location will be allocated and everything, a new object will be created. Okay, so that is immutable. However, maybe you are aware, but the thing is that they are not truly immutable. That is, came to know, that is the idea of this talk. Okay, before that, I would like to show like a runtime object state, how it looks like. So this is from objects.ch, object.h, from C Python code. So if you see the type defined structure is underscore object, we have a head extra, we have a object reference count, and the p type object. So object ref count is a part of the memory allocated for every object. So if you are seeing there, even though it is irrespective of the object is immutable, there is a part of the object itself, isn't it? And reference count is dynamic. So immutable objects are not really immutable actually, in reality, correct? Because it is having the inherent that property. So yeah, so that's what we came to know. Is immutable objects really immutable? Like we'll say that when I create a string, Aditya, I will say that for the whole life cycle of the, when my runtime is up, Aditya memory location will be similar and it is immutable. That's what we think, right? Till when this PAP came. So actually all objects are effectively mutable because of that data structure. Hope I am able to clarify that thing. Yeah. So that includes immutable objects like none and str instances also. Even the none, true, false, these are they are singletons. Even though they need to pass through that, when the object creation happens, they need to pass through with that same cycle. And think about that, when their creation is happening with that thing, they need to pass through the GC cycle also. So that should be not needed. So this is because every object reference count is frequently modified as it is used during execution. Also, for for containers, the runtime may modify the object's PyGC head. So there is one object's data type is their PyGC head. These runtime internal state currently prevent fully immutability. So, for example, like which I've shown to you, like let me just go through it. Here, see, the reference count is increasing and decreasing. So this means that this string is not immutable actually in reality. And how it impacted with our need of highly scalable applications, it impacted a lot. We'll discuss about it. So yeah, so proposal for PAP 683 came. Proposal was to create an immortal object by making a special value in object reference count field. So somehow we need to tell, just assume that if you would have been a designer, what you will be doing, first of all, you will be saying that, okay, the reference count should be out of scope for my immortal objects. If you are saying truly immortal objects, let them move out of the reference count. There should be no op. Obviously, as a designer, if you think, reference count should be out of the scope for the immortal. And ensure the core object state will never change. Means not a single thing should change for that object, not a single. That's what we say immutability. Also, allows the runtime to determine when it can or cannot mutate. Okay, so I'll reiterate. Currently, the C Python runtime maintains a small amount of immutable state in the allocated memory for each object. Because of this, otherwise immutable objects are actually mutable. This can have a large negative impact on CPU and memory performances. We'll see. Specifically for approaches to increase Python scalability. This proposal mandates that internally CPython will support marking an object as one for which that runtime state will no longer change. Consequently, as a designer, such an object's ref count will never reach 0. And thus the object will never be cleaned up. So, so that's why I explained about the object lifecycle to you guys. Now the question will arise, if it is not being cleaned up, if it is not GC, who will clean it up? So it will be cleaned up during finalization. Okay? That's why I created that. I started with very basics. Normally, only a relatively small number of internal objects will ever be immortal. Actually, the important part is that relatively very low number of objects we would like to make immortal. Will show, like none, Boolean. Okay, so these type. So, so the structure of an immutable, immortal object looks like this. So the introduction of immortal object come into picture. Till now, if you see that in the left-hand side, even for any object, irrespective of mutable or immutable, GC header and reference count are mutable. That is hence proven. But immortal objects, it is being defined that nothing should be. So I wanted to just show through picture. GC header, reference count, object type, and data. Everything should be immutable. With standard objects, a user can guarantee that it will not mutate its type and or its data. Immortality adds an extra guarantee that the runtime will not modify the reference count or the GC header represent. So move out of everything. No need of going through that cycle. Enabling full object immutability. What are the motivation for this PAP change? Why to immutable? So, so there are three major things happened which motivated Python community, specifically Meta and Insta, which they propose this change. So first thing was reduce CPU cache invalidation, avoiding data races, and avoiding copy on write. Let's go refresh on those topics also. It will be good to understand. CPU cache invalidation. As we know that data should be near as much as possible to CPU, correct, for fast access. So we created many cache memories, L1, L2, L3. And data, so the thing is that, as you know, the von Neumann architecture, the basic architecture, hard disk, main memory, cache, and it should be, the data should be near to CPU. So just assume that Python object, we created a Python object and we assume that it's immutable and we put in the cache. However, and many threads or processes are accessing. Somebody changed the reference count. Reference count will change certainly because they'll be creating, when we are assigning a new value, a new variable, descoping, anything is happening. Here, Python object is like type is string, as in the right-hand side. Value is hello Python, reference count 3. Okay, all good. However, reference count become 2. What will happen? It will say that, okay, it is not matching. Cache miss happens. The data is not coherent. What it will do? Again, we need to push the whole object's data again to cache. So the idea is, the write must be propagated to other cache levels and to main memory. This change has small effects on all Python programs, but on top of that, but if we are planning for multi-core applications, we have to pay a price in that scenario if this thing happen. When I talked about like if 2 threads are simultaneously working on, running simultaneously or distinct codes, are interacting with the same object, and this thing happens. So, so now immutable objects are really needed. Okay, that is one first motivation. Avoiding data races in multi-core. So this is, I tried to just picturize this, like how it looks like. Even we say that multi-threading is in place, but what happens is like multiple threads are, sorry, what is happening? So multiple threads are being spawned, and we think that, okay, we have a multi-threaded program, but in reality, GIL come into picture. We'll discuss about it is a hero or a villain. We'll discuss about it. Global interpreted lock, Python. So it allows only one thread at a time. So here, based on the immortal objects, we are considering making the GIL a per interpreter lock to enable true multi-core parallelism. So assume that GIL will go downwards towards per CPU or per interpreter, okay, which enables true multi-core parallelism, which is not present right now. Currently, the GIL prevents race condition between threads that modify the same objects. So it boils down to the same thing, same object, we are changing, race condition will apply, and data incoherency will happen. So we needed this immortal objects. So I would like to throw some more light on, like, if we are going to go per interpreter GIL, not a global interpreter lock, means per interpreter lock if we are going. So one of the solution would be each interpreter can be having its own copy of every object. This includes singletons, none, true, false, or static types. But the alternative to ensure that all said objects can be truly immutable or immortal. In that scenario also, that state is not going to change, we are safe, right? So the motivation was to avoid data race in multi-core. And this is also important thing, avoiding copy on write. So basically, many companies, like big sort companies, they are, to get the parallelism, in Python, what they are doing, they are working on pre-fork web server architecture, where what they will do, they will put the programs with their objects, shared objects, in one place, and they spawn the threads, processes, okay, worker processes, like it is being depicted here. And so, for example, Instagram rely on a pre-fork web server architecture to cache as many objects as possible and have each separate process use them as read-only structure through shared memory. That's what I try to put in a picture. So one thing is each process would be having a private memory also, which I have not depicted here, though obviously. And shared memory is like some of the objects they already put over there, like shared objects. While this greatly happens, upon closer inspection, they found that their process private memory usage grew over time, while their shared memory decreased. Why it happened? So you may be aware like why it was happened, because copy on write was happening. So why it happened, I will explain. Because the objects were not truly immutable. Their reference count or GC header was changed. And due to this, the workers process, the data was incoherent, and copy on write state that the property state that if the data is changing, you need to make a copy of that particular object and your own copy. So in that scenario, shared memory will be lesser used, and private memory of worker process will be increased use. So that's how it looked like in Instagram case. So we can see this memory usage. Left is private memory, it was shooting up, and shared memory was going down. This should not be the case. Shared memory should be up. Okay. So yeah. So Immortal Objects came in rescue. So as you can see, the data was showcased by Instagram in public, the data, and it increased shared memory usage through Immortal Objects, allow them to significantly reduce private memory and reducing the number of copy on writes. That makes sense. So what is the specification of this PAP chain 683? So as I already given a hint, so add py immortal ref count, the magic value. I'll show the magic value. So also I would like to tell that every object in C Python, they need to go through with this whole cycle only. Like they need to go with the pi increment and pi decrement function to increment or decrement the reference count. So what they have suggested, update pi increment and pi decrement to no op. If they found like it's just a condition check, if the magic number reference count is there, so the code will see that it is an immortal object, and do not do anything, no op. And also do the same thing for any other APIs which is using that count. Also stop modifying PyGC header. And the important part is that all the important immortal objects are cleaned up during runtime finalization. So code snippet I will quickly show up. This is how it looks like with the 3.2 version of Python. It looks like this is the latest in the code from 3.12. So you unsigned integer of max is being added as a pi immortal refcount. It is taken from the code base itself. I took the snippet. And this is also added. Okay. So in order to mark an object as immortal, its reference count is set to a special value. In case of 64-bit systems, this is done by setting the low 32 bits of the reference count field, which effectively sets the reference count of immortal object as the magic number, unsigned integer, and it comes with 4294967295. This is for pi side reference count. We'll say that, okay, do not set, do not do, do not take, do not worry about the reference count. Do this. Okay. So I believe the time is over. Thanks a lot for joining me. Yeah. Yeah. So these are the references and this. And yeah, maybe slides I'll be sharing. It has, if you have any questions or feedback, you can ping me in LinkedIn or email. This is my Gmail ID. Thank you. Thanks a lot, guys.